I'm consenting. Okay. So this is demo problem. Boop. (5-2), and this is page 146. Awesome. So this is telling us that we've got some production function, that there's some quantity, right? And it's a function of the amount of capital and labor that we have available. And it's an even mix. It's k to the 1/2 or k to the 0.5 times L to also the 0.5. Which,
can I ask you a quick question right there?
please.
And you said sometimes these 0.5 could vary. It's not always going to be 0.5s.
It's not always, right. So
when did you say they would vary?
So that's actually a very good question, and I can find out really quick what is. So there are values, they can test this kind of stuff, and I'm going to get it wrong if I pick, I'm going to get it backwards if I pick. Okay, so the labor share of national income, right, which is essentially what this is saying here, it's like how much labor goes into national income, has been pretty constant. So we can go ahead and we can real quick share this screen, right? So this is that B. So the labor share is about 2/3. And this is the actual data over time. So it's not always right on the button, but since 1960, it's been around 2/3, right? It's been around this 0.66. So, and it's just, you know, for convenience, right? So a lot of times you will see, a lot of times you will see these equations instead as k to the 1/3 and L to the 2/3. So
and that's Cobb-Douglas?
And that's Cobb-Douglas, yeah. I mean, Cobb-Douglas is I think technically Cobb-Douglas is any function where they're multiplied together and there's exponents that add up to 1, right? So it's always, they always have to add up to 1.
Okay.
That's part of, that's what makes it a specific Cobb-Douglas production function, right? I'm pretty sure, I mean, this is a Cobb-Douglas general, but the one that was developed by Cobb and Douglas is, yeah, so the general, to make it any Cobb-Douglas, it has to be something that's y equals a to the, oh, I was wrong. No, I was right. A to the k to the alpha times L to the 1 minus alpha, where alpha is bounded between 0 and 1. So, okay, you know, since alpha plus 1 minus alpha is always going to be equal to 1, right? Always, by definition. So that's a Cobb-Douglas. And we've been doing this kind of production function stuff for a long time, but it really wasn't until the second quarter of the 20th century, right? So, you know, the kind of interwar period, right, between World War I and right after World War II, did we start looking at economic production in this particular way. And then later on, somebody came along and said, well, it's not just the capital stock and the labor, it's actually the human capital as well. And so that's something that I don't think we get into in this textbook, but that's kind of like the most leading theory of what's called growth theory, national accounting theory, is saying that essentially there's another term in here. I mean, this A is our total factor productivity. So this is essentially, you know, how well we use our technology and labor. All right, so back to the task at hand. So we're given this equation here. Boop, 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 boop. And we're told if capital is fixed at 1, so capital fixed at 1, how much labor should the firms employ? How much L? So it's essentially, you know, choose L such that to maximize the profits, and remember we use that pi symbol for profits, maximize the profits when the wage rate is $2. And so this is a very important piece of information, right? We need to know the cost. All we know right now is we know the production, and we know that we already have capital and that it's fixed, and we're assuming no rental rate of capital here. So there's an assumption here, no rental rate of our capital, right? We own that money ourselves. We didn't have to borrow it or whatever. So the way to solve this is we're going to set the marginal product of labor equal to the wage rate. Now, why is that the way to solve it? Well, all right, I'll just have to do it live. So we're trying to maximize this profit, right? And what is this profit? This profit is going to be our total revenue minus the total costs, right? Mm-hmm. And so our total revenue, well, what is that? Well, that's going to be the production of the good, right? And we're told that the good is $10. I forgot about that. The price is $10. So we've got $10 times price times quantity, right? So I'm just going to go ahead and just fill in my production function right here, right? Times K to the 0.5 times L to the 0.5 minus, and then what are my costs? Well, my wage rate is $2. And so we're just going to have this equal to 2. So it's going to be minus $2 for every quantity of labor, right? So we're assuming that this is, you know, labor hours. And so, again, I was talking about, you know, how in economics, you know, there's usually some kind of function, there's some maximum, right? We want to find out where is that point. Well, the easiest way to find that point, if this is the function and this is the derivative, if we take the derivative, we find that the derivative crosses 0 right at that point where there's the maximum. And so if we're going to try to find the maximum of this profit function, and we know that it's some weird quadratic thing like this, the way to do it, instead of, you know, having to plot it out or put it in a graphing calculator or something like that, right? The way to do it is we go ahead and we take the derivative of it with respect to, so remember, we only have one axis here in terms of what our input is, right? This is our output. This is our Q. That's our Q prime. That's our rate of change of the output. But what's over here? This is labor, right? So why is this one labor? Well, because they told us the capital was fixed. And essentially, we can only work in 2 dimensions, right? So we know that this is actually a 3-dimensional problem, right? We know that there's a Z dimension, right? There's an X, Y, and then there's a Z that sticks out behind it. That's the capital, right? And we know that, you know, and we know that this thing is actually more like a mountain, right? That, you know, do the best I can. That's the leeward side of it, and this is the side that's close to us, right? And so it's a 3-dimensional object. Oh, that's way too thick. Rainbow pen's gonna be too thick too. Okay, so but we're essentially taking a slice of it, right? We're just slicing through and just looking at one particular you know, part of this mountain, right? So if we look at it from, if we look at this particular thing from the advantage of capital and labor, if we kind of split it, right, and then we have the quantity going out here, right, it's looking like a big kind of mountain thing, is what I'm trying to say. And we want to try to find that peak of that mountain. And the way to find that peak of that mountain is we're going to take a certain cross section where K is equal to 2. And that's what we get right here, is the cross section when K is equal to 2. Some weird, you know, quadratic thing that has a maximum, right? And so again, you know, we don't know what the maximum is. The best way to find out is we take the derivative and we set it equal to 0, right? So again, ton of economics is taking the derivative, setting equal to 0. So I'm trying to teach you why we do this thing, right? We do that thing because it's a shortcut, because this is what's going on underneath that shortcut. And so we're going to go ahead and we're going to take the derivative with respect to just the labor. It's distracting. So we're going to take the derivative of the profit function with respect to labor. And what does that mean? Well, that means that we're going to treat this K as a constant, okay? So what does that mean, I'm treating it like a constant? Well, if the production function had something that was in here like minus 5K, that would be the same as something that was minus 50, right? And we know that when we take a derivative, and if it's a constant and it's not attached to anything, right? It's not attached, there's no L here, right? And since we're taking the derivative with respect to L, it's just a constant, so it just goes away. So the derivative would just be 0 for both of those terms. And so when it's attached to an L, like it is over here, right? When it's attached to an L, then we just kind of leave it alone. We just let it chill where it's at. So 10 times K to the 0.5 times 0.5 times L, and here's where it gets a little tricky, to the 0.5 minus 1. So remember, we got to do that power rule, right? Even when we get a negative number in the exponent, right? And I'll show you what to do with that negative number in the exponent in a second. And so now, since we do have two like terms here, right? We've got a 10 and we've got a 0.5 in this equation. Everything's multiplied by each other. So we can take that 10, multiply it by that 0.5, so we end up with 5 K to the 0.5 times, what's this going to be? L to the negative 0.5.
I think I got, where did you get the 0.5 before the L?
That's a great question. So, so this part here is from the power rule, right? So since we had this equation here, since we started with this guy,
Okay.
and this is the exponent for the L,
You just
and
brought it down.
we're
Yeah.
treating the K as a constant. It's just like in a box that, you know, we're just treating kind of the same as the 10, right?
Okay.
It doesn't play an active role in the derivative. And then afterwards, you know, if it can combine with something cool, if not, that's fine too, right? So after we take the derivative, then we kind of assess and we say, okay, we've got this 0.5 that came from here, right? The 0.5 came from right there because of our power rule, right? When we have x squared, then the derivative of that is 2x to the 1. And so in a similar manner, when we have a x to the, we could do something else, right? 1/3, right? Then the derivative of this is going to be 1/3 times x to the what? And then again, this is going to go negative. 1/3 minus 3/3. And so it's 1/3 times x to the negative 2/3. And what do we do when we have stuff that's negative like that? Well, we can just put that in the denominator. So we can end up doing 1/3 times 1 over x to the 2/3. And then we can combine these things together and we can get 1/3 x to the 2/3 there. So that's just kind of a little aside in terms of the power rule when you end up getting a negative number, right? It ends up being a little wonky, especially fractions and stuff, right? We're usually not very comfortable with fractions, which is why I think the book tends to kind of stick to the 0.5 thing, because they realize that this is already like difficult, you know, so they're not trying to like complicate it any further. So, okay, so we end up getting 5 times k to the 0.5 times L to the negative 0.5, right? And we just saw what we can do with that. We can go ahead and we can simplify it and have it be 5 times k to the 0.5 over L to the 0.5. And then if we want to, which you might see it like this, so just for completeness, you can put both the k and the L in parentheses, and then they're both to the 0.5. Just like weird algebra rules that we never use. So that's the first part, right? We're taking the derivative with respect to the labor of the profit function. Okay, so the derivative with respect to this labor, right? The derivative of the profit with respect to the labor. Okay, so now let's go ahead and we got to remember that, you know, this isn't just a limitless production, right? There's diminishing returns to production. Otherwise, we could feed the whole world with just one flower pot, right? So there's diminishing returns. And so what are those diminishing, what does that mean? Well, that means that there's some kind of cost associated with it, right? And so we're told that it's $2 per hour. So we have a minus 2Q. And so we have to take the derivative of this. What's the derivative of minus 2Q?
Would it just be 2?
Yeah, very good. It's just going to be minus 2. Very good. And so, remember, what are we doing at the end of the day, right? Well, we are, no, I'm not trying to, no. Dude, I need you to cooperate a little bit more. So at the end of the day, what do we do? We're trying to find this maximum point, right? And so we're taking the derivative, and it's important, we have to set it equal to 0, right? It's not good enough to just take the derivative, right? So, okay, cool, yeah, we have the derivative down here, and it's all cleaned up, right? This is the derivative. So this is, what is this telling me this is telling me the rate at which profit increases when labor increases by 1. And so again, we're trying to, find that high point, right? So we have to take it and we have to set it equal to 0. So we're going to take this and we're going to do our last kind of step here. And again, this is the long way to get to our shortcut. And I'll show you the shortcut and how it relates, right? We're going to set this equal to 0. 0 equals 5 times K over L to the 0.5 minus 2. We're going to add 2 to both sides. And we're going to end up with 2 is equal to 5 times K over L to the 0.5. Now, this right here, now it's just a plug and chug, right? We're going to put, and I'll help you. Well, let's just do it. So we're going to come back to this point, though, because this is the wage is equal to the marginal product of labor, okay? So the shortcut has you skip all those other steps. Does that make sense?
Yeah.
But let's go ahead and just solve this real quick, right? So it's going to be 2 is equal to 5 times, we're going to plug in K is equal to 1 over L to the 0.5. And now we have a little bit of a pickle to kind of get out of here, right? We've got to get this by itself, right? We've got to get this second part by itself. So we're going to divide both sides by 5. So we end up with 2/5 is equal to 1 over L to the, and I'm just going to switch to fractions just because it's probably going to be easier for me. And then how do we get rid of a 1/2? Well, we use our exponent rule, right? So x to the 1 over a to the a power is equal to x to the 1. So the only way to free this from its little prison of being square rooted, right? I mean, this is really just the same as 2/5 is equal to the square root of 1 over L. 1/2 just means the square root. So how do we get rid of a square root? How do we get rid of a to the 1/2 power? In both of those situations, we're just going to go ahead and we're going to square what's going on there, right? But we can't just square what's going on one side of the equation. We have to square what's going on both sides of the equation because it's the seesaw and it'll get unbalanced otherwise. Squaring this is kind of easy. You just square both terms in the fraction. So it's 4 over 25 is equal to 1 over L. And then from here, it's just a matter of kind of flipping everything over, right? So we can multiply both sides by L. We end up with L times 4 over 25 is equal to 1. And then we can go ahead and how do we get rid of this fraction? Well, we can multiply by 25 over 4. Because then the 25s cancel out, the 4s cancel out. So we end up with L is equal to 25 over 4, which is equal to our 6.25 units. So 6.25, that's the amount. That's where the derivative is crossing 0 in terms of labor, in terms of the profit. And that's where we're going to have the maximum amount of profit when our capital is fixed at 1. Does that make a bit more sense now?
Yeah.
Okay. So when we're using this, we just have to do that last bit, right? We skip a lot of this intermediate bit by just knowing that, and so how can we do that? Well, fundamentally, let's take this equation. We know that we're setting the derivative equal to 0, right? So what's the derivative of the total revenue? It's marginal revenue. the derivative of the total cost is marginal cost. So we know if we're setting this equal to 0, then that means that our optimal, right, our Q star or our L star or K star, whatever it is that we're looking at, right, is where we're just going to add marginal cost to both sides, right? Since this is 0, if we add marginal cost to both sides, it annihilates it over here, and we end up with this condition of marginal cost is equal to marginal revenue, which I'm sure you're used to seeing the other way around, but it doesn't matter. Same thing. So it's just coming from this, we know it's some kind of parabola. We know it's some kind of quadratic function, right? We know it's a mountain. We want to find the height of that mountain. The easiest way to find the height of that mountain is to figure out when we stop walking upwards, right? When the derivative, we can think about this as, you know, your ascent change, you know, going up a mountain or not. And this is when you're coming back down the mountain. Right, you have negative movement along that elevation. Does that make more sense?
Yeah.
Okay. And so yeah, so the book's answer just jumps right to take the marginal product of labor and set it equal to the wage, right? And it says that since, so the book kind of, you know, it's using the shortcuts, right? So it's saying, okay, so since we have Q is equal to K to the 1/2 times L to the 1/2, then I know that that means A is equal to 1/2, B is equal to 1/2. I'm told that, you know, K is equal to 1 by the prompt. And so as a result, I'm going to go ahead and I know that my marginal product of labor is equal to A times K to the B times L to the A minus 1. And so since K is 1, you know, the square root of 1 is just 1, right? So MPL is equal to 1/2 times 1 to the 1/2, which is the square root of 1, which is just 1, times L to the, since A is 1/2, again, we end up getting a negative there, right? Whenever we are going to get a negative, I just go ahead and switch it to a fraction, just because it makes it a little easier for me, right? And so I end up with 1/2 times 1 times L to the negative 1/2. And so we have to set the, and so I actually made a mistake here earlier, apologize. It's not the wage is equal to the marginal product of labor, it's the wage is equal to the value, V for Vendetta style there, right? Value of the marginal product of labor, right? So what's the value, if this is the marginal product of labor, so MPL is equal to 1/2 square root of L. And so since we know that the price is equal to 10, and we know that the value of the marginal product of labor is nothing more than the amount that you contribute towards that price, it ends up just being 10 times 1/2 times the square root of L, or 5 divided by the square root of L. And so then when we set this equal to 2, why are we setting it equal to 2? We're setting it equal to the wage because that's our marginal cost. And so we're going to set it equal to 2. And so then we have 5 over square root of L is equal to 2. We're going to multiply each side by square root of L. That's gonna cancel out. We're gonna end up 5 is equal to 2 times square root of L. We're going to divide both sides by 2. We end up with 5/2 is equal to square root of L. How do we get rid of the square root? We're going to square both sides. And again, squaring a fraction is kind of easy because it's just 5 squared over 2 squared. This cancels out the square root. 5 squared is 25 over 4. That is our L star. That is our profit maximizing L. Does that make more sense now?
Yeah.
Okay, great. So now let's go ahead and tackle that problem. So we're given the same production function. So we're told Q is equal to K to the 1/2, L to the 1/2. We're told that capital is fixed in the short run. We are given a per unit rental rate of capital. Rental, I can spell. So before we were not given a rental rate of capital, right? And so that's what threw you off, right? So this is going to be $25 per unit of capital, per unit of capital. We have a wage that's going to be $15, again, per unit of labor. We're told the variable cost of using 81 units of capital and 9 units of labor is the variable cost.
And the same exact one, there's one that says variable costs, and then there's one that I think has something different in it.
Yeah, let's look, hold on, let me find. Are the costs that change when output is changed? So it's just anything but fixed costs. So it's asking us the variable cost of using 81 units of capital and 9 units of labor. So so this tricked you, and this asked you what just the variable cost was, right? Which is essentially just the labor, right? They tell you that capital is a fixed input, right? I mean, that's by definition though. And so the variable cost is going to be the $15 times the 9 units of labor, which gives us the $135.
Oh man.
I know, it's as simple as that. I know. It's always a bummer. Here, let me try to find one more before we wrap up for today.
Can you put it back on that quiz? I think there was one more.
Yeah.
That's exactly like that, but it didn't say variable.
Yeah, I'm trying to find it. Total cost.
So I think you might have skipped it. Go back a couple. No, it was a little bit right there.
Suppose the production for good X is characterized by the following production function where K is fixed input in the short run, the per unit capital rate R. So it's exactly the same stuff. Now it's asked for the fixed cost. Exactly the same stuff. So asked for the fixed cost, and the fixed cost is anything that is not a variable cost, anything that is a fixed input in the short run. So only capital here. Labor is only a variable or only a fixed cost when dealing with salaries and contracts. For the most part, it's a variable cost.
That one, I think I just took the 25 times the 81.
So this one would be 25 times 81. Very good. Yeah. So the fixed cost is equal to the capital times the rental rate of capital. So it's going to be.
I thought I had to do the whole other equation you just showed me.
Well, we learned stuff though.
Yeah.
We learned stuff. So I mean, that's the core of why we're taking those shortcuts, right? Is essentially there's a curve. We're trying to find where the rate of change is equal to 0. We're trying to find and these are shortcuts. The setting the wage equal to the value of marginal product of labor, setting the rental rate equal to the value of the marginal product of capital. Those are going to be the shortcuts when you're asked to maximize profits, right? So these things were just kind of giving you all the information, and then yeah, you didn't even use the production function at all, period, you know? So it's funny. I'm glad we went over the stuff we went over. But yeah, these were relatively simple, right?
Yeah. So on this quiz, one last question. I know I'm over my time, but I sort of didn't do very bad. I missed 2, but so I got like 13 out of 15, and I think you gave me 9 out of 15 on my grade.
Oh yeah, I'll fix that. Hold on, I'm trying to. How do I? This thing. I don't want to pause the share. Hold on, let me just real quick and then.